Okay, we have completed our experiments and we got some results. Now we got a sulfuric acid from the cleaner reacting with the baking soda. We'll address that first. Then we have peroxide decomposition catalyzed by potato slices. We have a dye that gets oxidized by bleach at different temperatures, resulting in different speeds of reaction. And then we have a solution that goes from colorless to pink when you transfer it into ice water. So let's take a look at the acid reaction first. So this is what we got for the acid reaction. We got a concentration of sulfuric acid. And the sulfuric acid is from drain cleaner. And one of the concentration is C and the other one is 4C, meaning one concentration is 4 times higher than the other. These solutions were reacted with baking soda. And then we got the different rates. This concentration C reacted between 9 and 10 seconds. The 4C took between 2 and 3 seconds. So we can clearly see a pattern. It looks like the concentration is affecting the rate, and 4 times the concentration is increased. You increase the rate by about 4 times. We can conclude this could be like a first order reaction. So here we can have a rate, and then we have a rate times 4 here. Times the rate, when we have 4 times the concentration. The way we write the result is called a rate law. This is what we conclude. We conclude that the rate of this reaction is equal to some constant which we have to determine experimentally. We needed to. And the concentration of H2SO4. And this is raised to the first power, but the first power is not normally written. So that will be the form of the rate law that you will get in the experiment by looking at the concentration changes and see how the reaction changes. But normally we need something called the integrated rate law. This is called a differential rate law. This is called the differential rate law. So what we do is we do a simple substitution just to simple things. We call the H2SO4 just simply an A. We're going to call it A. Normally we call it A. When we have done this substitution, we can rewrite the equation. The rate we rewrite it as dA dt that's equal to minus K, and A is the concentration of the acid. After you do that, what you do is you pass the T's to that side and the A's to this side. From that you get dA over A is equal to minus K dt. After that, you set up the integration to convert this to the integrated form of the rate law. And this dt goes from 0 to t, and the integration limit in here is from A0 to A, where A refers to the concentration at the beginning of an experiment. From that, what you get is that the integral of this expression is natural log. So we have natural log of A growing from A0 to A is equal to minus K T. and this goes from 0 to t. After you do that, this is what you get as the final answer. That the natural log of a minus the natural log of a0 is equal to minus k. But then we can write it in some other format. See, you're mostly interested in this. You're interested in obtaining a concentration and then getting a rate based on that concentration that you are given in a question. So to do that, we will have to write it into another format. So let's go up there. Let's erase this. And leave that so we know that this is what we are doing. So we convert this into natural log. So we put 1 on one side. So normally the concentration at any time is what you put on this side of the equation on the left. And then on the other side you have concentration at time 0. Or whatever the term is. In this case it's a natural log. Okay, again, we're not supposed to use calculus to pass the chemistry class. So let me just give you a quick explanation. When you have a reaction rate that is first order, this is the kind of data that you would get. So this will be the time axis. And then that will be the concentration axis. So this is like an A. And then over time, the rate is going to change. So let's suppose you start here, and then at some period of time, the concentration gets depleted, and it gets depleted depending on the amount of stuff that is left. So if you start here, let's suppose the depletion rate is 50% over time period, you will end up here. After that, the depletion rate is still 50%, but now you have less of that because it's 50%. Then you, sorry, it will be around here. So it's 1/2 of that. On the next time frame, you will get 1/2 of what you had. Then you will get 1/2 of what you had, and so on. So this is the kind of graph that you will get from the first order reaction. And then if you look it up in a mathematics book, the integral of that kind of graph, that will be like 1 over x. This is 1 over concentration. Just look for 1 over x, and you will find that the integral is the natural log of x plus a constant. So that's basically all we need to know. So another thing that we need to know, and I guess we should really learn this, because this is going to be around in more than one topic for the general chemistry class, the natural logs. So the natural logs are functions that fit natural phenomena, and that's why they're called natural logs. And then let's suppose you have a normal log. Right? So it would be a normal log. Normal logs are base 10. Natural log is Ln. Ln is base E for Euler number. Then when you want to perform the anti-calculation, the anti-log, this one, you will need a 10 to the x. That's the anti-log calculation for a normal log of base 10. But then if you have base E, you do the exact same thing, but then the base is not 10 anymore. you need to perform a calculation of e to the x. That will be the anti-log version of the natural log. So let's write that equation that we have there in another format. So you want to write it in terms of the concentration, not natural logs. You will have to do the anti-log of that. So let's do that. So we'll go from here and do the anti-log. Anti-natural log operation. And then what we get here is that instead of natural log of A, we get A. Instead of natural log of A0, you get just A0. And instead of minus Kp, you get e to the minus Kp. So these are the two equations that concern you for the first order reaction. That will be the integrated form of the first order kinetic law. So this is the kind of formula that you will get. You will do in an experiment involving that sulfuric acid reaction with the baking soda. You will conclude that this was a first order reaction. But the first conclusion is. And is first order with respect to the concentration of sulfuric acid. So you will replace the A with the sulfuric acid concentration. And it will be 0 with respect to the baking soda, only because the baking soda is used in a solid form. And we don't have enough time to explain all of that right now, but that's the way it is. It will be 0 order with respect to baking soda. And then you will conclude that it's a first order reaction, and this is the way you will have written it in the differential format. Then when you do the integration, this is what you will get. And you want to normalize it even further. You just put the concentration on one side, the concentration at any time, and then the concentration times 0 on the other side, with whatever factor will be a multiplier. And then after that, in here, because we got logs, natural logs, we want to take the anti-log to make the formula neat. Okay, so that's how you get the differential rate law from an experiment. And this is how you get the integrated rate law. So let's look at another example. So that's where we got the answer from. We got that when we have certain concentration of sulfuric acid, then we got some rate of reaction. And then when we increase the concentration of the sulfuric acid, we got a different rate of reaction, which was even higher. So that was a first order reaction. We concluded that the reaction rate was influenced by concentration, and we can write that as a rate law. And the differential rate law is how we express that information. But then the integrated rate law is the one that really gives us what we need. So as an example, let's just try a theoretical example of those of a rate law that would be similar to the potato catalyzed into the composition of peroxide. It's not very obvious at the start, but it's kind of similar. So let's consider a reaction, and we're going to put the data in a graph. Okay, so the graph, and this will be the axis. And this will be the concentration axis, and we are talking about CH3, CH2, OH, which is ethanol. So we're talking about ethanol concentration. We have some units for that. will be in millimolar. So ethanol concentration in millimolar. So I want to consider a concentration that is in the range between 0 and 100. So that would be 50. I'm writing a different color so it's easier to see. So this will be 50. This will be 100. And then here we will have 20, 30, 40, 70, 80, 90. Okay, so we have a mid-axis here. Then what is the time frame? So we're talking about alcohol getting depleted in the human body and then making some byproducts that are not as toxic as the alcohol. The time period for such a process will be in the range of hours. So we're going to consider here an experiment carried out over a period of 8 hours. So that's 4, 8, 6, 2. That's 1, 2, 3, 4, 5, 6, 7. So that would be the kind of data that we would get. And we found that the depletion follows this pattern. First thing we need to do is we need to take some points that are easy to read. This will be kind of easy to read here. So we're going to take those points and then base our sample calculation on that. So what we have here is ethanol concentration in millimolar getting depleted over a period of 8 hours, going from 100 millimolar to 0 in 8-hour time. And then we get a reaction rate there. And then we're going to see what the rate constant is first. So the first thing you need to do is, in an experiment, you have to find a rate constant. So for that, we take the concentration 1, concentration 2. So we get the concentration 1 as being, we start from 100 millimolar. So that would be a good one. Concentration 2, we go to 50 millimolar. And then we have to match this with the times. So we get the concentration 1 with the time 1, which is time 1 equal to 0 hours. And time 2 is equal to 4 hours. Okay, so now we got the data that we need to compute the what is called a rate constant. This is how you get a rate constant. So we get the concentration and the time. So what to do is, in here we want the change in the concentration over the change in time. And for that, what we do is we do the standard way, the way you will do a slope calculation. It's like a slope calculation. So we start with the number 2 data set. So concentration 2 is 50 millimolar. Time 2 is 4 hours. Then we subtract the 1 parameters. Concentration 1 was 100. And the time 1 was 0 hours. And let's see what we get. So we get 100 minus 150, the difference, and with our time. So we get 12.5. So this is what we get. We get a depletion rate of 12.5. That will be negative because of the depletion rate. That will be millimolar for every 1 hour. So we get millimolar per hour. We don't need to write the 1 there, but just leave it so we know that it's per 1 hour. So we get a reaction rate constant of 12.5 millimolars per hour. This looks like as a differential format. We get that the change in concentration over the change in time fits a formula here. So we get the change in the concentration. Okay, so we're gonna do it in the standard way. We call it A again. That would be the ethanol. We want to keep things simpler. Over the change in time is equal to minus K. So that's what we get from the differential rate law. It says here that this is a minus K, and we don't have anything here in parentheses. We don't have the concentration of ethanol there. The reason why that is because in here we see that the rate is a constant over a period of time, even though this millimolar concentration of ethanol is dropping, the reaction rate is still the same. So we have a situation here where the reaction rate is independent on the concentration of that reactant. So what is that? We are going to get a conclusion in a moment. First, what we need to do is we have to convert this into the integrated format because we would like to answer a question. Given a time, let's suppose you pick a random time that is not a nice number. Let's say 2.67 hours. Would you be able to tell me what concentration of this ethanol at 2.67 hours? And it will be a tough question to answer given that differential rate law, but if we have the integrated format, we could answer the question. So we do the same thing we did before. We put the A's on one side, and then we take this dt dividing and multiply it here. Then we do the integration again. That's from 0 to t. And this integration is from A0 to concentration A. Okay, so now we got our setup. And then we're not going to write the limits of integration again, just go straight because we saw what they are. And what we get here is that the integral of that would be concentration A minus concentration at time 0 is equal to minus K T. So that would be the integrated format. Now, what we have to do is we have to put it in a form that gives us the answer we are looking for. Normally, the question asks you about initial concentration, but more often than not, you are given some concentration that after certain amount has reacted. So we would like to leave this concentration here and equate it to that. So this is a minus A0 becomes A0 here, and this minus KT. And then we just write the little question here. what is the concentration of CH3, CH2OH ethanol at time equal 2.67 hours. Yeah, 2.67 hours. So that's the question that we can answer now that we have the integrated format of the rate law. And in a moment, we are going to see what kind of reaction this is. This happens to be a zero order reaction. Okay, so a zero order reaction will fit perfectly with this example, because what's going on here is that, let's suppose the person gets really drunk, now they are intoxicated, and then the liver is starting to process that alcohol to turn it into something that is not toxic. But then the liver has some enzymes, and at this point, when somebody is highly intoxicated, they are all saturated with alcohol. The enzymes are working as hard as they can, and they have reached the maximum limit, right? What is called a turnover number. And then they are working as fast as they can. The rate cannot go any faster, and that's it. So that's why when we get a zero order reaction, when the reaction is, in this case, a biological catalyst, or another example would be any type of catalyst, such as a surface. When the reaction is a surface and the surface gets saturated, then there is a limit to how fast the reaction can go. After the reaction goes to the maximum speed, no matter how you change the concentration, you are not going to make the reaction go any faster. So let's write this constant here on the side, that K is minus 12.5 millimolar, because we're going to need that in a moment to answer that question. So we clear some space here. And what we need is, we need this. We need the integrated format of the rate law, and then that will give us the answer straight away. Okay. So what is the concentration? What is that? At time equals 2.67 hours. Okay, so right here, this is the concentration that we are looking for. And this is equal to what the concentration was when the experiment started. Let me write it in a different color here so it's easier to see. So this is not the same as this. This is the one at the beginning. And this is what we are looking for. That will be minus KT here. So let's see what we got. So that will be equal to, the concentration at time 0 was 100 millimolar, minus KT, 12.5 millimolars per hour. Okay. 12.5. Okay, so and you can see there clearly that the hours would cancel. Let me write this in a way that gives more room. So that's equal to the concentration at time 0, which is 100 millimolar, minus Kt, which is 12.5 millimolars for every 1 hour, times T. And then time T is 2.67 hours. And you can see clearly that according to the dimensional analysis method, those hours cancel, and then your answer will be in millimolar. That's what we get. So we got 12.5 negative 2.67. So we get 66.625. That's kind of trying to get too exact when it's not. The concentration of CH3, CH2OH concentration at that is 66.695. At time 2.67 hours. Okay, we know if it's right or wrong. Okay, there is an easy way to test it. What you do is you can go to the original graph, even though you don't have the graph available when you're doing these calculations. Let's see if this millimolar almost matches that time. So that would be 60, and this would be about 66. Then we hit the graph, okay, and then we will bring it down here. So this is 2, 3, 2 point, like 2 and 2/3 almost. It's about 2.67. So yes, this is about 2.67. And this is approximately 66.6 millimolar, given the resolution of that graph. Okay, so we have the information we need for a zero-order reaction. This is an example of an enzyme processing some substrate. Now let's look at the results that we got. We got peroxide, fresh potato, catalyzed the reaction. We start to see a lot of bubbles. Cooked potato did not catalyze the reaction. Apple catalyzed the reaction at a slightly slower rate. And when we try to change the concentration of the peroxide, the reaction did not change that much. Right, so let's go over those results. So let's start with the last one. We say that the peroxide concentration of the peroxide okay, does not affect the rate. Let's say does not affect the rate. And we say that the rate is a reaction rate. So the concentration did not affect the rate, and the reason is because the slice of potato only has a surface, has a limited surface area where the active stuff is. We're going to that in a moment. And then it seems to get saturated when the concentration goes near about one half of what the pharmacy salt peroxide is. So that's kind of the limit of how much that potato can process. If you increase the concentration of peroxide, you will not see too much of an increase in the reaction rate. Let's look at the potato cooked. So what we have there is we have fresh potato. And we have cooked potato. So first of all, what we have is we have something called an enzyme, and the enzymes have some metal ions. So the metal ions are connected to amino acids. So it's a chain of amino acids, the way a protein is. And then this metal is in an environment that is very different from solution. What makes it so special is that these metal ions can change between two or more oxidation numbers reversibly, and that facilitates electron transfer reactions, like the ones of the peroxide decomposition. So we are imagining that this potato contains some enzymes, mostly catalase, although there is other proteins, as long as they contain a metallic redox center, they will do the job just fine. And then that's what the fresh potato is using to catalyze the reaction. So the catalyst increases the reaction rate. Normally the peroxide would fall apart, but very slowly, too slow for you to see. And what about the cooked potato? So the cooked potato, we have that metal, and then the amino acids, they are not connected anymore. They are kind of all falling apart. So the protein fell apart once we cooked the potato, and that's what happened with the biological catalysts called enzymes. You cook them, they get denatured, they do not work anymore. So the cooked potato lost its catalytic activity compared to the fresh potato. And so that's the conclusion that we got from the potatoes. So we learned something. So let's move on to the dye temperature effect. So up to now we have seen the effect of concentration on the rate. We have seen that the catalyst speeds up the rate of a chemical reaction, and we're going to make a commentary of that in a moment when we get to the energy of activation. But this is pretty much what we need for the moment. So let's move on to the reaction rate effects from temperature. So remember that we just saw some examples of real rates, and then we got some rate constants. And when you see this type of question on an exam, or some example on the textbook, you will notice that when they mention a rate constant, they also mention a temperature. For example, the rate constant we just got will mention that it happened at physiological temperatures. Unless this guy has a serious fever, that will be around 90 Fahrenheit. So the reaction is happening at that temperature, and then the rate constant is valid under those specific conditions. The rate constant will change with temperature. So that takes us to another topic. First, let's write what is called Arrhenius equation. So at first, you don't need to understand what it is. We're going to go step by step on the different components. So what we have is that the rate constant is a rate constant in the Arrhenius equation, is equal to some number labeled A and an exponential term, and that exponential term is negative. Important to remember, it's negative, and that number is energy of activation divided by RT. So at the moment, don't worry about it. You do not know what those numbers mean. We're going to go step by step, and we are going to conclude what they mean. First of all, let me introduce you to some concepts. In the PowerPoint, we saw a graph. Okay, so this was the kind of graph that we saw in the PowerPoint. And then there were some numbers being distributed, and this is the number of particles. And this is their kinetic energy. So what kind of numbers do we get? The kinetic energies that are found on those graphs are usually in the range of tens of thousands. So we're going to write here like this is a 10,000 for this example, 20, 30, 40, about 50,000, 60,000. I'm going to leave it at that. And this is in units of joules per mole. So we got a graph that is called the Maxwell-Boltzmann distribution. Right here is the Maxwell-Boltzmann distribution. And the Boltzmann distribution is based on something called the chi-square distribution with 3 degrees of freedom. So you don't have to understand all of those concepts right away. It suffices if you understand that the chi-square distribution is just a probability distribution. It's something from statistics. And then, so this will be based on the chi-square distribution with 3 degrees of freedom. And the 3 degrees of freedom only comes from the fact that we are looking at some model that treats our molecules the same way. They are kind of spherical objects, so they have 3 degrees of freedom. The 3 degrees of freedom means it can move this way and that way, left and right, that's 1 degree of freedom. It could move up and down, that's another degree of freedom. And it could move in and out of the board, that's the 3rd degree of freedom. So this is where the 3 degrees of freedom comes from for those particles. So the Maxwell-Boltzmann distribution is based on the chi-square distribution with 3 degrees of freedom. You don't need to know the entire equation for this, right? What you need to know is you need to know certain parts. So let me just write this so you can see it. That whatever this graph is has certain similarities with what this Arrhenius equation is saying. So this function here is based on an equation. The equation is 4 pi, right? M is the mass of all particles, that's uppercase M. 2 pi RT. This R is a constant. It's an energy constant. We're going to look at in a moment what the value is. This will be the absolute temperature. So this is to the 3/2. And then you have a factor B squared E. So again, the E comes in. You see the natural log base. And then we get the exponential factor, which is the kinetic energy over RT. So we got the uppercase M B squared divided by 2 RT. So this is the kinetic energy, 1/2 mv squared over RT, which is the energy of the particles based on their temperature, the absolute temperature of the system of particles. So you don't have to try to understand every single term in here, right? What you need to understand is that this equation generates a graph, and then the Arrhenius equation takes from that graph to draw some conclusions. So let's see what that chi-square distribution with 3 degrees of freedom looks like. It looks like this. And I think it's a bit pumping here. Okay, that's what it will look like. The chi-square distribution with 3 degrees of freedom, and then we are distributing here kinetic energy between a number of particles. So the area under the graph is the total number of particles. And then if you were to take a piece of the graph, right, let's suppose you take between here and there. So in here we will have 20,000 and 30,000. So this will be particles with energy between 20 and 30,000 joules per mole. That's what you will have if you were to take all the particles that are under the curve on that region. So the entire region of the graph is equal to 100% of the particles. And if you take some section of the graph, you're taking a fraction of those particles. So let me just label another one. Let's suppose we label this right here. We label this number, and we call this an energy of activation. At the moment, we don't know exactly what that is. Okay, you don't have to know exactly what that is at the moment. We're going to call it an energy of activation. And normally we label it uppercase A, EA, energy of activation. So now we know that the chi-square distribution is what this Maxwell-Boltzmann distribution is based on. We know it has 3 degrees of freedom because of the 3-dimensional motion of the particles, with every 3 dimension equally probable. And we know that this graph is generated by this formula. And we don't care much about the rest of the formula, but what we can see here is that in there is an exponential term. The way that exponential is Euler's number. And then it has a kinetic energy divided by RT term. And as you can see here, that's almost the same thing we have here. Just that in here we have a specific number. We don't have a kinetic energy generic. We have a specific energy here in the Arrhenius equation. So now let's see what those numbers mean. So let me write this. So this K will denote a rate, a reaction rate. So let's take a look at different situations, and we're going to put some numbers so that it becomes more clear. This is clear if you put numbers on it. Without numbers, it's kind of meaningless. So in here we have these numbers. We have 50,000, 40,000 here. 40, and this is 1,000. And these are all thousands. 10,000, 1,000, 1,000. So we have 40,000 labeled on that graph, and we're going to use that 40,000 to illustrate what it means in terms of the Arrhenius equation. And then from there, we're going to interpret the results we got for the oxidation of the dye when the temperature changed. So in here we have a rate. So let's suppose this is just a rate. And the rate, we're going to express it in reaction between particles per second. Right? So we're going to put a generic number here. And we're going to say that this is like 1.5 times 10 to the 12. So this is just a random number. Is you can use another number. It's just that seems like a reasonable number for this kind of situation. That will be the number of reactions between molecules happening per unit of time. So if everything was perfect, this is what this would be like. If everything was perfect, that would be equal to the number of collisions between two particles A and B types. So we are saying here that we are having some collision number. Let's suppose 1,000 collisions per second. The number is a lot bigger there, but let's just suppose that we have a plain number like 1,000, and we're saying that every one of those 1,000 collisions results in product formation. So everything is perfect, and this number is equal to that number. So the rate will be equal to the number of collisions that you have. But nothing is perfect. There is some factors that affect the success of the collisions. So let me just give a quick example here, something simple. Let's suppose you have a particle, some kind of molecule, and it has a little circle here and then a triangle. And then you are reacting it with a particle that is kind of like a little circle. Then the product that you get from there, if you get product, it will be this circle, triangle, and then a little circle attached here. So in that simple picture, you can see the implications of this. What we're saying is that when this particle hits here, it is hitting it in the wrong place. But when this particle hits here, it's hitting it in the right place. So in order for the reaction to take place, this circle has to hit the triangle. If the circle hits the other circle in the molecule, there is no reaction. So here we have no reaction in that instant, and in here we get a reaction. And as a result, in the simplified example that we have that every particle that hits the other type of particle has a success rate of over 50%, because if it hits the upper half, nothing happens. If it hits the lower half, then the reaction happens. So we have a situation where we have a 50% success rate. So this number will change now. We have a 50% success rate. So now that number is not CAB anymore. Now we have another factor to worry about. We have the number of collisions between A and B, those two, and then we also have a static factor saying that the number of collisions that we have does not mean that we get those numbers of reactive particles. Only 50% of them are going to be successful. Then if we have that kind of situation, this number will drop now. Now you are going to get 7.5 times 10 to the 11. You don't have the same reaction rate anymore that you were predicting based on just collisions. Now you have to worry about the static effect of the collisions, and now the reaction you predicted is not correct anymore. It has been cut by 50%, only because of the static factor. But in the Arrhenius equation, we put these two together, and we call it A. So at this point, we have that this is 7.5 times 10 to the 11, and that is equal to A, which is equal to also 7.5 times 10 to the 11. We don't write the units here just to keep this simple, but you know it's like collisions per unit time. Now, this will be a perfect situation. We are saying that this is the high temperature limit. Okay, so why do we say that? If you write the rest of the Arrhenius equation, this is what this equation is introducing. Now, you have a rate constant that is equal to the number that you computed, and then you took into account static effects. But now you have another factor to worry about. You have to worry about this number, e to the minus energy of activation over RT. The energy of activation is this number we labeled here. It's telling us is that there is an energy barrier for that reaction. Going back to the catalytic reaction, this is what we have here. We have a reactant, and it goes to product. Sometimes the energy is lower here, and sometimes it's higher. But it doesn't matter if the energy is lower or higher. You always have to worry about some energy barrier between the reactants and products. So this is independent of whatever the reaction produces or releases energy. There is always an energy barrier. So when we were doing the potato experiment, what we had was that the reaction did not have to go through the energy barrier. So that will be catalyst. So the catalyst did not really make the energy barrier go away. The energy barrier is still there. What the catalyst did, provided an alternate path for the reaction. So now the reaction doesn't have to go through the same steps anymore. Those peroxides are just attaching to the surface of the potato, and the reaction mechanism is completely different now. So we cannot really say that the activation energy barrier just got lower. Actually, there was another path where the energy barrier is lower. So that's the activation energy concept, and that's what we have introduced here. So what does that number do? This number here will be a multiplier. And on the high temperature limit, that number is equal to 1. Okay, so let me explain that. So we can try this on a calculator. Try this. You take the as t goes to infinity, just it becomes very large, doesn't really go to infinity. Then this term E minus energy of activation over RT goes to 1. Okay, you need proof, I guess. So all the proof you need is you try to perform the calculation on your calculator. Try making the E very tiny, or just make it 0. And this is what you get. When the number that the E is raised to becomes equal to 0, then the number approaches 1. So in the high temperature limit, whatever you got here stays. The reaction rate is still 7.5 times 10 to the 11 based on the collision number and the aesthetic factors. And that will mean every single molecule that collides in the correct orientation is going to result in a product. Every single one of those molecules contains an energy that is equal to or greater than the energy of activation. That will be in the high temperature limit. So how do we do that? Okay. So this line here, we're going to draw a black line, and this will be a higher temperature. So we get the same graph, but the graph shifts. The graph is shifting. And now what we have is that if you increase the temperature, you have a larger number of particles that have the kinetic energy required for the reaction to happen. But then if you have a very high temperature, really, really high, then this graph is not here anymore. All of the particles just have a lot of energy. Everything is right there. So that's what the high temperature limit is. So what this is as a multiplier. So the E to the minus energy of activation over RT is a probability multiplier. I'm not sure if this is the correct term to say, but it's like it's a probability term in the topic we're discussing, because this is based on probability. So this is like a probability term. And then it tells you the fraction of particles with energy which is equal or greater than the energy of activation. Okay, so let me step aside for the second and can record some notes. So let me put some numbers into that so we can illustrate the concept. What we had in the experiment that we did, we had some dye, and then the color got completely annihilated in less than 2 seconds when the temperature was 40 degrees Celsius. It took like 3.5 minutes at 20 degrees Celsius. And when the temperature was near 0 degrees Celsius, we waited like 5 minutes and the color was still there. So let's look at the temperature effect on that number by putting some numbers on it. So let me read the top. I guess everybody got the notes they need. So leave the Arrhenius equation there. And now, to explain why the dye lost its color so quickly when the temperature was high, right? Let me just put some numbers into this so we can get a perspective. So let's suppose we still have a rate of 7.5 times 10 to the 11. So let's suppose we still have a 7.5 times 10^11, and then that number was obtained from the pre-exponential term. So this pre-exponential term is equal to that number. So now let's see how the number will change if the temperature is equal to, let's suppose, 273 Kelvin, which is the temperature of the cold die. And then we are going to consider the other one, which will be the hot die. That will be about 313 degrees higher. So we consider two temperatures, and then let me introduce to the constant. So the constant R is approximately 2 calories per mole. If you want an easy way to remember this, you don't know to get the exact answer, but then so that is equal to approximately 8.314, and that will be in joules per mole Kelvin. So this is times Kelvin. So this is a universal constant of energy. It tells you how much energy a particle will have based on the number of particles and the absolute temperature of the system of particles. So we're going to put this exponential term here, and we're going to take these two numbers and see how the numbers will influence the answer that we get there. So let's try the first one. So that will be, so an arrow here, E to the energy of activation. Let's suppose the energy of activation was at the 40,000 we already labeled there. We're not sure what the energy of activation for that reaction with the dye, the oxidation was. We're taking just a reasonable number. So that would be minus 40,000 over RT, which is 8.314, and the temperature is 273 Kelvin. No writing units, we just write the numbers to keep it clear. So we got 40,000, 8.314 to 313. And then whatever number you get there is going to multiply that number, and that is going to give you an idea of how the reaction rate changes. So this is the first one. So we have E to the minus 40,000 divided by the constant, 273 Kelvin. So we got this. We got 2.22 times 10 to the minus 8, right? That's the first number we got. 2.22 times 10 to the minus 8. Let's try the other number. So we get the same E number, minus 40,000 is the activation energy. We use the constant times, this time we're using 113 Kelvin, not 273. Then we get this. 2.11 times 10 to the minus 7. Now we take the ratio of the two numbers, and the ratio of those two numbers is going to give you the ratio of the rates. Okay. So 2.11 times 10 to the minus 7 over 2.22 times 10 to the minus 8. 2.11 times 10 to the minus 7 divided by 2.22 times 10 to the minus 8. Okay, you get a 9.5 there. So this is the conclusion. This is the way we connect what we just saw from the numbers to the die. Even though this is not exact because we don't know what the exact activation energy is. But then we can say that temperature increase of this one from that to that, that would be 40 degrees. 40 degrees. We just call them degrees. We don't have to specify what they are. Will increase the rate 10 times over. So that's what we got. We changed the temperature by 40 degrees from the hot to the cold, and then the reaction rate changed by about 10 times if this was the energy of activation. It's not exactly what we got in the experiment, but we did see that the temperature difference really changed the reaction rate of that dye. The blue dye disappeared almost immediately when the temperature was 40 degrees Celsius, and then when the temperature got lower, it stayed there for quite a few minutes. Okay, so let me clear the area. You can write some of those numbers if you find them useful, and we move on to the next part, which is the chemical equilibrium. So for the chemical equilibrium, we didn't have the chance to prepare a buffer, which is a good example of chemical equilibrium. We just prepare a solution that changes color based on the temperature changes. So for the buffer, we just want to consider an example here, and then we're going to take it from there. So first we have to introduce the concept of equilibrium constant. Let's suppose you have something happen in the gas phase, and then we have a compound that looks like this. Okay, it's just a molecule, and it has 3 atoms, and they are in the gas phase. And then the reaction goes forward and goes back. And then the product will be the atoms separated. So if you wanted to write that in another format, you will have n molecules here in the gas phase going to 3n molecules also in the gas phase. So when you have gas phase reactions, you don't use concentrations, you use partial pressures. So we'll just justify this for a moment. We don't need to learn the ideal gas law yet because that will be in another laboratory experiment. But this is where it comes from. This is the ideal gas law. Pressure times volume equals number of moles times a constant times the absolute temperature. If you solve that, you will notice that this here, N over B, when volume is in liters, is equal to a molar concentration. And that molar concentration, if you do the algebra here, is proportional to the pressure, and then you divide by RT to get the real number. That's why we can use partial pressure instead of concentration when we are dealing with gases. Okay, so we got two numbers to work with here. We have that the reaction going forward is 4.75 times 10 to the minus 3. We're not going to write numbers here because we don't, it doesn't really matter inside. We just want to see the numbers and put them into context. So we have 4.75 times 10 to the minus 3. And then we have 1.25 times 10 to the minus 5 going back. So we have skipped the units here just to keep things simple. This will be like seconds to the minus 1. If you want to be formal about it, just write seconds to the minus 1. But it's not going to change what we're doing. So let's suppose we have those reaction rate constants. Question first, how do we get the equilibrium constants? I think we mentioned that before. We mentioned that the equilibrium constant is the ratio of forward to reverse reaction. Forward to reverse, because the forward will be like the products, and the reverse will be like, say, in reactants. So the equilibrium constant is equal to forward over backwards. So we write that. So the forward is 4.75 times 10 to the minus 3, and the backwards is 1.25 times 10 to the minus 5. Was it right? 10 to the minus 5. No, it's 10 to the minus 1. Okay, so now we have set that up. We have a forward and backward reaction rate constant. And then we know that the equilibrium constant is going to be the ratio of those two numbers. And we just put the numbers together in a way as to get the ratio. Now we compute it. 4.75 times 10 to the minus 3 over 1.25 times 10 to the minus 1. And this is what we get there. 3.8 times 10 to the minus 2. So we get that this constant is 3.8 times 10 to minus. So that will be the equilibrium constant. And from that, now you can write an equilibrium constant expression. So what we have is that the 3.80 times 10 to the minus 2 is going to be the equilibrium constant, and that is going to be equal to products over reactants, and in here we're using partial pressures, so that will be the product has 3m, so the partial pressure of the product, we're talking about the product here, and then raised to the third power. So it's raised to the third power because in the product side you have 3 molecules or 3 moles, and on the reactant you have only 1 mole. So on the reactant side you will have only the partial pressure of that reactant. And from there you could answer a question, any question, given some partial pressure that you are given. What is the partial pressure of the other thing based on the equilibrium constant value and the one that is given? That's one thing. Something else to notice here is what we have is an equilibrium constant that is very small. So let's write some observational rules here. If the K equilibrium is larger than 1, then what you have is mostly products. If the K equilibrium is smaller than 1, what you have is mostly reactant. So what we have there is a 3.8 times 10 to the minus 2, a number much smaller than 1. And the conclusion is that we have mostly reactant. So let's try one example. Let's suppose you have 12 times 10 to the minus 3 atmospheres of the product. Find the partial pressure of the reactant if the partial pressure of the product is equal to 12.0 times 10 to the minus 3 atmospheres. So we're writing here the pressure in atmospheres. The main reason is because this equation is in atmosphere. The pressure is in atmospheres, so you keep things consistent. So we'll answer that question. I just clear the area so you can snapshot or whatever you prefer. Okay, so let's answer that question now. We have the equilibrium constant, right? And then we have the question. So what we have is that this equilibrium constant is equal to the product parts of pressure of the products to the third power over the parts of pressure of the reactants. And when one of the numbers, the parts of pressure of the reactant is the one we don't know, but we know the parts of pressure of the product is 12.0 times 10 to the minus 3 atmospheres. And then we write in a different color to remind you that this is to the third power. Okay. So now we just solve. So these two exchange places. This was here, and that one stays. So what we get is 12.0 times 10 to the minus 3 atmospheres to the third power over 3.80 times 10 to the minus 2 is going to be equal to the partial pressure of the reactant. Let's see what we get. So we get 12.0 times 10 to the minus 3 raised to the third power over 3.8 times 10 to the minus 2. 4.54, 4.55 times 10 to the minus 5. Okay, so if that is really true, you can inverse the operation and then you will get the equilibrium constant. Or you can use this as a given and then find this as the answer, if this works out. So we set it off with this as the unknown. So let's suppose this is the unknown, and then the other quantities are known, and we set off the equilibrium constant again. We have the K equilibrium is equal to 3.80 times 10 to the minus 2. Okay. And that is equal to the pressure of the product raised to the third power over whatever we are given, 4.55 times 10 to the minus 5. So the number that we got is in atmospheres. Then we solve. So we put this here multiplying 4.55 times 10 to the minus 5 times 3.8 times 10 to the minus 2. 1.73 times 10 to the minus 6. So we get that 1.73 times 10 to the minus 6 is equal to the partial pressure of the product raised to the third power. Now, and we get the same thing. 1.2 times 10 to the minus 2, which is 12.0 times 10 to the minus 3. So the partial pressure of the product is equal to 12.0 times 10 to the minus 3. So now we are going to introduce briefly the topic of Le Chatelier's principle right here, and we're going to kind of kill two birds with one shot, two pigeons with one shot, or whatever you want to interpret it, by also introducing the concept of chemical quotient. So let's take those numbers, and this is what we want to do. What if the partial pressure of this, right? This is partial pressure, changes. For some reason, changes. It will change if you remove some of the product. So let's suppose it changes to, let's say it's 8.5 times 10 to the minus 3 atmospheres. So these are atmospheres. And then I will ask you to tell me about it. Tell me about what will happen if I change that partial pressure for 12.0 times 10 to the minus 3 atmospheres to 8.5 times 10 to the minus 3 atmospheres. So let's see what happens. We write the expression again, but this is the thing. It will have a different name. It will have a different label. So we have here the partial pressure of the product, or the partial pressure of the reactants. So we're going to see what happens at that point in time when that partial pressure is getting changed. So we put the numbers. We take the partial pressure of the reactant, 4.55 times 10 to the minus 5 atmospheres. And then we take the changed value. Now the products will have a partial pressure of 8.5 times 10 to the minus 3 atmospheres. And then when you get this answer, it's not going to be called K equilibrium anymore. So this is not K equilibrium anymore. It has a different label now. Now it will be called the chemical quotient because it doesn't have the same value as the K equilibrium. Let's see what value it has, and then we're going to see the significance of that. So let's write it in the right format. So we get 8.5 times 10 to the minus 3 to the third power. 6.14 times 10 to the minus 7. We're going to skip the units here just to show you the numbers to see you get an idea of what they look like. And then we get this number here. So we get that number. (1.35 times 10 to the minus 2). Now compare it to the K equilibrium. 3.80 times 10 to the minus 2. Is smaller than K equilibrium, which is equal to 3.80 times 10 to the minus 2. So the chemical quotient. So what we're saying is that now the chemical quotient is a number 1.35 times 10 to the minus 2. You compare that to the equilibrium constant, 3.80 times 10 to the minus 2. And then you get that this number is smaller than that number. So in order to restore the equilibrium, the system has to do something so that this Q changes. And the way it has to change is that this number has to get larger now. To restore the equilibrium, the number has to get larger. And that's the basis of Le Chatelier's principle. When you change the system, you put some stress on the system, then the system will react to restore the equilibrium. So let's see what the system is going to do. So the situation we have here is that at this point in time, we have the reactant, and that was a molecule that was bound, going to product, which is this. And now we have removed this. That's where we say that we just remove some because we decrease the partial pressure of those products. Now what happened is that according to the Chatelier Principle, the system has to restore the equilibrium constant value. It doesn't have, mind you, it doesn't have to restore this number. It doesn't have to go to 4.55 and 1.2 times 10 to the minus 2 that we had before, right? Or 12 milliatmospheres. I picked the number because it's very simple to use. So the system does not have to go to those values. What the system has to do is it has to go towards products in such a way that some reactants disappear, some products form, and then the partial pressure, when you put them on that expression, is going to give you back the equilibrium constant. What if you did something different? Instead of this number, you change that number, right? You make this number smaller. Then the opposite will happen. Now, when you make this number smaller, the quotient number that you will get is going to be larger than the equilibrium constant. And then the system will react to make the number smaller to restore the value of the equilibrium constant. So that's the Chatelier principle for you. So we remove some, and the reaction is going back and forth. For a moment in time, the reaction has to move that way. Okay. So the reaction will move forward until the number that you are getting, the quotient, is equal to the equilibrium constant. So depending on what the number is, if the number is larger, then it will move to decrease it. If the number got smaller than the equilibrium constant, then the system will move to make it larger. Okay, so let's put this in simple terms here, just a tiny picture. So what you have is something like a system of equilibrium. Let's suppose you have a knife edge here. And then here you have some reactants. And here you have some products. So as soon as you remove some of these products, if you remove that, then the system is going to start making some more. You have to produce more of that. You can imagine that the reactants and products, whatever the value is of the equilibrium constant, it's like they are at equilibrium. They are equilibrated to the knife edge. Then if you remove something from one side, the equilibrium has to be restored by depleting the other side, taking it to this side of the other species until the numbers again match in such a way that the equilibrium constant gives you the same value as it was at equilibrium. So as soon as you make the change, you are introducing some stress in the system. Now, the equilibrium constant doesn't have the same value anymore. We call it the chemical quotient. And then this will start changing in the direction that will restore its value, K equilibrium. So now let's address the question about the experiment we did. We had a colorless solution. And then the solution could go back and forward between colorless and pink. It was pink when in ice, water. But it got colorless in in warm to hot water. So that's also the Chatelier's principle. But then here we are dealing with energy. So what we have to do here is we have to introduce two ways of writing the reaction. One of those ways is more useful than the other when you are answering the Chatelier's principle questions. So let's leave that. So we have two ways of writing a reaction that is sensitive to energy addition or subtraction. What we have is reactants goes to product. And then we have that the reaction has enthalpy change. And the enthalpy change will be the difference between two energy quantities. Goes from here to there. So if you have this type of change, meaning that you started up here and then you end up here in terms of energy content, what you have is the negative enthalpy. So when you have a negative enthalpy, what you are saying is that energy is a product. And that's how you write in order for these questions to be made a little easier. So we write it as reactants goes to products plus energy. And this will be an exothermic. And you will see how simple that explanation is for the solution that was changing color. So another possibility for the reaction, an enthalpy. So we have reactant goes to product. And in here again we have energy changes. But then this is in the opposite direction. At the end you have more energy than at the beginning. So what you get is that you have an enthalpy change that has a positive sign. And then we can write it as an endothermic reaction as reactant plus energy goes to product. So that's the second possibility that we have. And then we can easily see what the type of reaction we were dealing with was. It was colorless when it was going into warm water. It was pink in ice water. So remember that these numbers here, reactant and product enthalpy changes, refers to the particles that are reactants and products. Don't refer to the surroundings, right? Whatever is around it, that's not it. It's the particles that are reactants and products. In this case, what we have is that when we put it in ice, we are removing energy from those particles. And removing energy makes the solution grow pink. So the product, the pink product, is obtained by removing energy. So this is the type of reaction that we have. It's exothermic. By removing product, we did not remove the pink product. Energy is a product. And we remove some energy by putting the solution in ice. And that made the reaction go forward. When we add energy by putting the reaction in some warm water, then the reaction goes back to reactants because energy is a product. You are adding more product. In order to restore the equilibrium, you have to get rid of some of that product by making more reactants. So that will be the explanation for the solution that we studied at equilibrium. And the solution was turning pink when in ice water, and it was turning colorless when in warm water. Right, that concludes our lab for today. Remember to log into Blackboard, Collaborate Ultra. If you have questions, the line is open. Please stop by if you have questions. Let me clear.